name is Wang Yuchun, and I'm from Department of Chemical Science and Engineering in the Institute of Science Tokyo. I'm sure you have already heard the story how our school changes from Tokyo Tech to Science Tokyo now, so yeah, I won't explain it again. And the title of my research is Preparation of phthalocyanine nanoparticles by laser ablation in liquid and the application to perovskite solar cell. So first part is my introduction. Uh, the fast growth of the planet's population has caused an increase in energy consumption and an ever-increasing demand. It has been estimated that by 2050, the energy gap will be around 15 terawatts. And the increased consumption of fossil fuels to meet the energy demand is considered the main reason for greenhouse effect and global warming. So under these conditions, solar energy in all its usable forms gains more and more importance because it's clean and safe and inexhaustible and renewable. And one direct way to export solar energy is to convert it into electricity by using the solar cells. And perovskite solar cells, with its fast growth in coefficient efficiency, gets more and more importance these days. And the advantages of perovskite solar cell is it has low cost, flexible and lightweight, and the high temperature processing is not needed during the fabrication. And it has high currentability and high extinction coefficient. And we can see from this graph, the highest coefficient efficiency got by the perovskite solar cell is higher than the silicon PVC in the PV markets. And normally, perovskite solar cells has three main components. The first is hybrid organic-inorganic metal halide perovskite, which usually have a structure of AbX3, where AB is cations and X is anions bond to them both. And the perovskite work as a light absorber. And since many kinds of elements can form this AbX3 structure, the band gap are tunable by varying the stoichiometry. And the second part is the electron conducting materials, which is usually an N-type nanostructured metal oxide semiconductor. And the whole transporting material, which is usually a P-type material. And we can see from here, when the perovskite layer is irradiated by light, it will inject charge carriers into whole transporting materials and electron transporting materials. And the photocurrent will be collected from the front and the back of the device. And there are some traditionally applied whole transporting materials like these three, and they have some problem like high cost, hygroscophicity, and the dopant requirement to enhance the whole mobility. And this is what I propose, the phthalocyanine. You can see the structure of phthalocyanine here. And it can coordinate with many kinds of metals in the center. And the center metal will change its properties. And the advantages of phthalocyanine work as a whole transporting material is it has low cost hydrophobicity, and it has high thermal, chemical, and photostability. It also have high whole mobility and conductivity. And also it can enhance the film's crystallinity and the coverage of the perovskite. So I was trying to use the spin coating technique to make this thin film by distribute a solution on the substrate and rotate it at the high speed to spread it across the substrate, and after evaporation, you'll get your thin film. So you can, the advantages of spin coating is you can achieve precise thickness control by changing the spin speed and the time. And it's also very cost effective. And the process is also very fast. It will be completed within minutes. But we have facing some challenges when we are using the spin coating, because the spin coating requires uniform dispersion to ensure the thin film uniformity. But the problem is phthalocyanine does not dissolve well in the most conventional solvents. So I was hoping that maybe nanoparticles can provide the dispersion required for the even coating. So this is my research, the laser ablation in liquid method to produce the nanoparticles. it works like when the laser is irradiated on the raw material, it will be fragmented by the laser to form the nanoparticles. And the advantages of the laser ablation in liquid method is it's a very simple process. You just to get the laser on the particles, and it's no contamination, just the raw materials and the solvent. And the particle size are also controllable by changing all the laser conditions, and also the cost is very low. And the objective of my research is first to prepare the phthalocyanine nanoparticles by laser ablation in liquid method, then use it for spin coating and optimize the spin coating process to improve the thin film crystalline quality. And the next part is the experiment and the result. The first, I will introduce my experiment on the laser ablation in liquid. And the material I'm choosing is nickel phthalocyanine powder. It's the nickel in the center of the phthalocyanine. And the process would be first to put the powder into the DI water and treat with ultrasonication to get the suspension. Then it's for the laser irradiation. After that, centrifuge the product to get the nanoparticles. And after that, it's the characterization of UV-Vis, ACM, DLS. And you can see right-hand side is the perimeter of the laser. The wavelength is 532 nanometers, and the pulse duration is 13 nanoseconds. And the repetition is 10 hertz. And the fluence, which means the energy density of the laser, will be changed from 125 to 200 millijoule per square centimeter to see its effects on the result. And the concentration of the raw material is 100 milligram per milliliter. And the material chose is nickel phthalocyanine. And also the irradiation time will be changed from 15 to 60 minutes to see its effects on the result. And this is the result of morphology dependence on the laser fluence. We can see that the fluence is changing from 125 to 500 millijoule per square centimeter. And as we can see that on the first graph, on the first picture, we can see that when the fluence is not high enough, there will be some like string-shaped large particles exist. And as the fluence increased to 250, the large particles almost disappeared, and as the fluence increased, the particle size also decreased. And next is the size distribution. We can see that when the fluence is 125, it has a quite wide distribution. And as the fluence increased, the distribution become narrow. And this one is the particle size as a function of laser fluence. So we can see that the secondary particle size decreased with the increasing of laser fluence, which is because when the fluence increases, it will offer more energy, and which will promote the fragmentation to make smaller nanoparticles. And next is the UV-Vis result. We can see that it has two peaks at 618 nanometers and 668 nanometers, which is because it has two crystal structures, alpha and beta, and they have different absorption. And this is the peak absorbance as a function of laser fluence. We can see that as the laser fluence increase, the absorption increase, which means there are more nanoparticles produced with higher energy. And next one is the duration time changing from 15 to 16 minutes. We can see that when the time is not really enough, there will be some larger raw material like things existed in the samples. And as the time increased, they are disappeared. And the particle size also decreased with the increasing irradiation time. And next one is the size distribution. We can see that they are quite evenly distributed. And this is the particle size as a function of irradiation time. We can see that the secondary particle size decreased with the increasing of irradiation time. And also the UV-Vis shows that with the irradiation time increase, the absorbance increase, which means more time there will be more nanoparticle produced. And next part is for the spin coating. By distribute the solvent on the substrate and spin it to get the evaporation to get the thin film. So there will be 3 steps in my experiment. First is to choose a better solvent for the spin coating and to just the spin coating parameters to get the high quality thin film and the characterization of the thin film. Why I need to choose a solvent is because when I was producing the nanoparticles is in the water, and the problem with the water dispersion is the perovskite materials are very moldable to water, so it can't be used. And also the surface tension of water is too high and the evaporation rate is too low, which is not good for the spin coating. So I was want to change it into organic solvents because it can protect the perovskite stability and it has a lower surface tension than water, which will improve the film uniformity. And also it can enhance the compatibility with the phthalocyanine. As I said, the phthalocyanine doesn't dissolve very well in the conventional solvent, but it gets better in the organic solvents like water. And so this is the test for the solvent. So I was choosing chloroform, toluene, and hexane for the test. And the thing I do is first to put my nanoparticle dispersion to freeze drying to get the powder, and redissolve the powder into the organic solvent to see. Well, I get it for the ICM, but we can see by naked eye that it's dispersed much better in chloroform. So, but I still show you the ICM pictures because although it gets a good dispersion by naked eye, but you can see that there are many aggregations happened during this process, which I suppose is because it happens during the freeze drying process. So you can see that there are quite large aggregations, and even in the chloroform. I was thinking that if the freeze drying not work, I will find another way to get it from water into chloroform, which is I just put the chloroform into the water dispersion and stir overnight to let it transfer from the water into the chloroform and get this. You can see this darker place in the bottle it's the chloroform. And the reason why I get it centrifuge is because you can see the ICM, these are in the water and these are in the chloroform. We can see that there are still many large clumps of the particles that doesn't disperse very well. So after the centrifuge, we can get separated the larger ones from the solution and get this smaller one, which is better for the spin coating. And this is the process of the spin coating after contribute. I just take it to the spin coating. So these are the parameters I'm using. The spin speed is 1000, 1500, and 2000 RPM, and the spin time is 30 seconds. And the solution volume I use is 0.2 milliliters. And this is the AFM I got. So we can see that the spin speed changing from 1000 RPM to 2000 RPM doesn't change the deposition very much because the coverage is not really enough. So, and I also did UV-Vis to see the optical properties, and the blue one is for 1000 RPM and the red one is 1500 and the purple one is 2000. We can see that the spin speed increased, the thickness, candle thickness decreased, which is reasonable because when you speed it too fast, it will get, the less of the deposition on the substrate. So this is kind of the problem I'm facing now, but I get quite a lot inspiration from McLaughlin group, and I think I can do something to improve this spin coating process. So next part is the conclusion. The nickel phthalocyanine nanoparticles were successfully prepared by the laser ablation in liquid method, and with the increase of fluence, the particle size decreased, the absorbance increased, and with the increase of irradiation time, the particle size decreased and the absorbance increased. And the nickel phthalocyanine thin film were not very successfully prepared by the spin coating techniques. So my future work would be to adjust the spin coating parameters to improve the film uniformity. And hopefully I can succeed, and then it's performing the Hall effect measurement to evaluate conductivity. And that's all. Thank you for listening.
Earlier, you mentioned about the if you could go to the place where you first introduced phthalocyanine. On the slide, I think it's slide 4, slide 5. Yeah, the one after this one, sorry, the whole transport material. So so you mentioned that it is quite hydrophobic. How does that specifically aid this particular material as a whole transporting layer?
Well, the traditional structure of the perovskite and the inverted. When you use the inverted, the whole transporting material will be on the substrate, on the perovskite. So if it can protect the perovskite layer.
Okay, all right then. Yeah, that's my main question really. Thank you.
Any more questions?